Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss hysteresis or BS curve and energy loss due to hysteresis. Let's begin. Let we consider a ferromagnetic substance. Ferromagnetic substance, an example of a iron bar. And we plot the graph between B and H B along y direction and H along x direction. And that ferromagnetic substance is placed in a magnetizing field. We have to magnetize that ferromagnetic substance as an example of a iron bar. The magnetizing field is slowly increased, then the intensity of magnetization also increases. Let me show in that of graph. When H gradually increases, at that of a point intensity of magnetization also increases. Therefore, S increases, then B increases. At a point A, there will be no such further increment of a B as S increases. That one is the saturation stage. Again, if we decrease H, then B gradually decreases, and at H is equal to 0, B does not 0. There will be some value of B, and that value of B, this portion is known as retentivity. Again, if we increase S in the negative direction, B gradually decreases and finally at a point B will be 0 or some negative value of S. Again, when we increase the negativity in S, it gradually increases in the negative of that of B, and finally we achieve a saturation point. That is the stage of saturation. Saturation stage. Then ultimately, if we decrease it, at that of scenario, S does not 0 when B is at 0. Again the cycle continues. We named it as O A point as G C D E F, and that portion where the magnetizing field S in the negative direction required to make B as 0 is called coursivity. Coursivity. This portion is known as retentivity, that portion is known as coursivity, and the entire cycle is known as the cycle of magnetization. The cycle A G C D E F A, that is the cycle of magnetization. The cycle of magnetization, and the closed curve like A G C D E F A. In that way, that process continued. The closed curve A G C D E F A is known as hysteresis loop. Hysteresis loop. And the process throughout there will be the lagging of magnetization B, here B lags behind that of magnetizing field H when the ferromagnetic substance is taken through a complete cycle of magnetization is called the hysteresis. The process the lagging of magnetization B behind the magnetizing field H when the ferromagnetic substance is taken through a complete cycle of magnetization is called hysteresis. Hysteresis, that is the lagging of magnetization B behind the magnetizing field S when that ferromagnetic substance is taken to a complete cycle of magnetization is called hysteresis. As you understand it. Now, for clarity, let I draw that graph as the hysteresis curve. Hysteresis loop, graph between H and B. Okay. Next, energy loss due to hysteresis. Mathematically we study what amount of energy is lost during the process of hysteresis. Let we consider a ferromagnetic sample that have unit volume. That unit volume is taken through a complete cycle of magnetization. Here let we choose, let small n number of atomic dipoles per unit volume and mu m the magnetic moment of dipole and theta be the angle between mu m and magnetizing field H. Magnetizing field H. The magnetizing field H, where a ferromagnetic substance is placed and it has the magnetic dipole moment as mu m, which creates an angle theta to that of H. When we resolute it, we obtain mu m cos theta and mu m sin theta. The magnetic moment mu m can be resolved into two components. One is mu m sin theta and another one is mu m cos theta. Here mu m sin theta is perpendicular to H and mu m cos theta is parallel to H, or we can say that is along the direction of H. Since there is no magnetization perpendicular to H, therefore mu m sin theta will be 0, since there is no magnetization perpendicular to H, so that the sum of all components of mu m, that is perpendicular to H, is 0. That is summation over mu m sin theta will be 0. Next, there will be only contribution due to mu m cos theta, which is along the direction of H, that is the magnetic moment per unit volume. Here all the summation is the magnetic moment per unit volume. These are perpendicular to field H. In the same way, the summation of mu m cos theta, the magnetic moment per unit volume, the magnetic moment per unit volume, that is intensity of magnetization, which is the magnetic moment per unit volume. We taken which are parallel to field edge. It is intensity of magnetization I is equal to summation over mu m cos theta. That is the only contribution of mu m cos theta. Since mu m sin theta, sum of mu m sin theta will be 0. The intensity of magnetization is due to summation over mu m cos theta. Equation number we choose. Equation number 1. When I is increased, intensity of magnetization is increased by a small amount. That small amount di. Then di is equal to its differentiation. So d summation over mu m cos theta, or di is equal to summation over mu m differentiation of cos theta, or di is equal to differentiation of cos theta minus sin theta minus summation over mu m sin theta. Equation number 2. Here negative sign means, negative sign indicates I decreases at increase of theta. I decreases at theta increases. Let me calculate the torque acting on that of magnetic dipole. That magnetic dipole is placed in that of magnetic field S. What will be the torque? Torque acting on magnetic dipole placed in magnetic field H. Tau is equal to mu m cross H, or tau is equal to mu m H sin theta. Equation number 3. The work done when we rotate that of torque. Work done when dipole rotates through an angle, small angle at d theta, is given by minus d theta. dw is equal to tau into minus d theta, or dw is equal to minus, in place of tau it is mu m h sin theta d theta. Value of tau is put here, or dw is equal to h minus mu m sin theta, that is nothing but di h di. Equation number 4. The small work done, then total work done is calculated by integrating that one throughout that of complete cycle of magnetization. Total work done is taking a substance, taking the substance and ferromagnetic substance through a complete cycle of magnetization. Is total work done W is equal to integration over closed curve dW, complete cycle of magnetization, which is S di. S di, that is the closed curve integration. We obtain area of that BH loop, BH or IH loop. Since B is equal to mu naught H plus I, therefore dB is equal to mu naught dH plus di. Now multiplying both sides by h, when h is multiplied, h dB is equal to mu naught h dH plus h di. Here multiplying h on both sides. That mu naught is divided here, h dB divided by mu naught is equal to h dH plus h di. Therefore h di is equal to h dB by mu naught, that in this side is minus h dH. h di is nothing but dW. dW is equal to h dB divided by mu naught minus h dH. The equation number 5. Now we put this value to evaluate the total work done. Therefore work done during one complete cycle of magnetization is W is equal to closed curve integration over dW, which is 1 by mu naught closed curve integration over h dB minus closed curve integration of h dH. Here closed curve integration over h dH will be 0. There will be no such term, only h dB. So 1 by mu naught closed curve integration over h dB. As we know, W is equal to 1 by mu naught times closed curve integration of h dB, that is the area of the hysteresis loop or BH curve. The work done 1 by mu naught times that of area under that of curve. Hence, energy loss per unit volume during one complete cycle of magnetization is equal to 1 by mu naught times the area of BH loop or hysteresis loop, and that energy loss appears in the form of heat. Loss of energy appears in the form of heat. The energy loss per unit volume during one complete cycle of magnetization is equal to 1 by mu naught times of the area of that BH loop, and this energy loss appears in the form of heat. Here, with the help of this video lecture, we understand the concept of hysteresis, or we can say it as BH curve. What is retentivity, coercivity, cycle of magnetization, hysteresis loop, and the phenomenon of hysteresis. And mathematically, we show what amount of energy is lost due to the process of hysteresis. We consider a ferromagnetic sample of unit volume, and that is taken through a complete cycle of magnetization. Then calculating the energy loss, finally we obtain the energy loss per unit volume during one complete cycle of magnetization, which is equal to 1 by mu naught times of the area of that BH loop, and that energy loss appears in the form of heat. So, with this useful and informative notes, let me wind up this session. Thank you.